welcome. Take a seat and grab something nice and warm to drink, like my water chino here. It's just water. Today, I want to talk about a piece of maps that made my day a while ago, and I think it might just make yours too. And it's to do with probability and stats, one of my favorite areas of maps. And it's to do with this connection between the mean, median, and mode. I remember in school I was taught about the mean, median, and mode, and that there are different ways of measuring center. But it seems like the median and mode are a bit underappreciated, or at least I underappreciated it. Since later on, when I learned more about probability, we keep talking about the expected value. We keep talking about the mean. We kind of forget about the median and mode. And here is what I think a missing link in that story that I discovered recently. So let's start. We have some random variable x, which means that this is a situation where we have a random experiment or a random situation where x, this random variable, could take different values depending on when we look at it or how we look at it. It will take different values, and how it takes different values, the randomness of the different values, depends on what x is. So x could be really spread out, or x could be not so spread out. For example, if x were points on this page, the first time we look at x, it might be here. The second time it might be here. Third time maybe here. Fourth time maybe here. Fifth time maybe here. And so it's what we use to model randomness. And the expected value of x is a constant fixed point, which has this special property from the weak law of large numbers, that if you were to look at x n times independently, and you were to take the average value of x, then this converges to the expected value of x. So what it's saying is that if you look at x many, many, many times and take its average position, then eventually you won't be able to distinguish it from this special expected value, which here I'm going to say was the cross. So that's kind of maybe why expected value is so useful, because of this property. But I don't really know, so well, join me as I think about this. What we could do now is think about measures of center. So the expected value is, in some sense, a measure of center, since this sample average tends to it. But we could generalize it a bit. We could do it in a way that's, I think, talk about center in a more intuitive way. And the way we do that is by talking about the expected value of spread. So what I mean is, let's take a constant big C, and I'm going to call that A, be a center. And we're going to look at an expression of the form the expected value of D of x and C. The center is a constant. And here, this D is going to be a metric, or D is going to be a measure of distance. I haven't really studied metric spaces, so this will be exciting for me when I do. And we could pick different D so that we will be measuring a different kind of spread. So this expression is saying the expected spread of x from C. And what we would like to do is find a C, and that for a particular metric would minimize this expression, minimize this expected spread. Then that would give us a good idea of what it means to be a center. That you could expect the random experiment, the random variable, to not spread from it too much. So let's consider a few different Ds. I've drawn this, specially prepared this nice diagram. And here we have three different metrics. We have the green, the purple, and the orange. The green is the metric is the squared distance. So if we're interested in some the distance from some constant point, the spread from some constant point t, then, and we've sampled x1, x2, and x3 from our x, then the green squares, the area of the green squares, would represent the distances, the spreads of the samples from our fixed point. So you could see that as our sample goes farther and farther away from t, this metric grows really, really quickly. That the square, for x3, the square has a tiny area as it's close to t, but x2 has the square with a huge area. So this is a square distance. Okay, another choice which I think is more natural is the pink. I put pink because pink is pretty, and I think this is pretty. And the pink metric is saying, just take the straight line distance between x and t. So that's represented by the lengths of these pink lines. So you could see that although x2 still has a bigger spread than x3, it's not as crazy as for the green areas. And finally, we have the orange. The orange crosses. So the orange is like a silly metric. It's saying this is a measure of distance where if you have 1, if x is exactly on top of t. I messed it up. Let me fix that. It should be your distance, your spread is 0 if you're exactly on t. Otherwise, it's 1. So it doesn't really care. It doesn't really distinguish between these three, as none of them are on top of t. Okay, so let's go for it. Let's start with the expected value of x minus t squared. Let's call that x minus c now, for c for center. Find c that minimizes. Okay, so let's do this. I'm gonna first do this trick, which is this. Look at what I'm doing. So I've just messed up the bracketing. Let me try that again. I'm gonna do the mathematician's trick of writing 0 in a clever way. I'm gonna subtract an expected value of x and then add on an expected value of x inside the bracket. So you can see that these two are the same, but this is just new. And I've done this because it's a nice way of rephrasing what I mean when I say spread of x from c. I'm saying that to go from x to c, I could first go through its expected value. Going from x to c is the same as going from x to expected x, and then from expected x to c. So x to expected x is this first term, and expected x to c is the second term. Okay, let me grab another piece of paper and we'll continue this. So now I could expand. And that I'm going to use the FOIL rule and treat each of these two distances as separate things. So I have a squared plus 2ab then plus b squared. Right. So the expected value of this thing. And because expected value is magic, it's linear. I don't really know why it's linear. If any of you know, please tell me. This is bothering me. This has been bothering me for ages. So that means we could take the expected value of each thing separately. And the first term here, the expected value of this is actually just the variance of x. Actually, that's just a fancy way of writing it. The second one here, well, we have an expected value of x minus the expected value of x here. That's going to be 0. The expected the spread from x from its expected value is 0. And the second term is going to, well, just be this because it's a constant. Expected value of a constant is a constant. So we're left with this nice expression. And all we notice is that this is a constant, this is a square. So that means that this is minimized when c is equal to x. This is the unique minimum. No, when c is equal to the expected value of x. This is the unique minimum. It gives this beautiful alternative interpretation of the expected value. That it's the unique point, the unique constant that minimizes the expected spread if we're using squared distance as our metric. And if my proof seemed like magic, that's because it is. This trick of writing 0 in a clever way, it kind of shows up in many proofs, and this does give an intuition for it, and you could see that the key part was that this happened, that we had this x minus expected value of x, which we knew, which would become 0. But actually the original way I did this was longer and used calculus and things, and I would say wasn't as nice. But that may be a more natural way to figure this out. This was like this morning I was like, whoa, I could instant solve it. So if you were to do it the calculus way, you would consider something like this. Times, you would consider something like this. Oh no, not this. Like x minus c squared times this. And then you could split it up and differentiate and do all kinds of cool stuff with it. But here we'll just finish there. Yeah, so now we'll take a break, and then next time we will talk about the other metrics.